Okay, so without wasting the time, I'll start the lecture. So just there was huge gap between previous two lectures and today's lecture. So we have seen general concept of the control system, some its parameters, requirement, what is the control system, like it may be open loop, closed loop. Later on, we have to consider the disturbance parameters into the control system, as well as we have seen the conversion of time domain and the frequency domain. Later on, we have seen certain signals where we have computed its Laplace, say S domain, then the Laplace transform and its properties. Today we'll start with the next, that is inverse Laplace transform. So I'll share my screen. I hope the screen is visible. PPT. We'll start with the inverse Laplace transform. Is it visible to you? Somebody may reply.
Yes, sir.
Yes, sir.
Okay. So
Yes,
again,
sir.
you may have, yes, you may have learned these concepts or these properties into the mathematics. So instead of skipping that, we'll just go somewhat faster to this topic. So the inverse Laplace transform. Inverse Laplace transform is used to convert S domain to the time domain again. So what is the inverse Laplace transform? Inverse Laplace, simple, transform a function S domain back to the time domain. So, and this is the function x of s is the S domain, can be transformed into the time domain x of t. If Laplace transform of x of t is x of s, then the inverse Laplace transform by definition is x of t is equal to inverse of x of s. Inverse Laplace transform of x of s will be 1 upon 2 pi j integral of e raised to power st x of s ds, where L inverse shows the inverse Laplace operator. Laplace transform need not exist for all x of s. This is the definition. Then properties of inverse Laplace transform. Finding the Laplace transform of x of t following the basic definition is cumbersome in many cases. It will be somewhat difficult, of course. To simplify the process, certain properties of Laplace transform have been derived from the definition. In practice, a Laplace transform are obtained by the application of one or more of these derived properties. So inverse Laplace transform properties, suppose x1 of s is the function where its inverse Laplace transform is x of x1 of t, x2 of s, its inverse Laplace transform is x2 of t. Then linearity property, I have added one constant to x1 of s plus b x2 of s. So its inverse Laplace will be straightforward. That is a x1 of t plus b x2 of t. Then time shifting property is, suppose we have Laplace transform signal that is x of s. Its inverse Laplace will be x of t. Then suppose time shifted will be x of s minus s0. So its inverse Laplace transform will be e raised to power s0 t into x of t. These are simple properties. Later on, there will be certain examples wherein you will say get it clear. So suppose x1 of s, its inverse Laplace is x of t. Then x of as, that is time shifting or time scaling, its inverse will be 1 by a x of t by a. Then time reversal, it is very straightforward. X of s its inverse Laplace transform is x of t. If I do time reversal, that is x of minus s, then its inverse Laplace will be x of minus t. Then multiplication by s property. So x of s is this, its inverse Laplace is x of t. So we multiplied x of s by s, so it is will be multiplication property. So s x of s will be, its inverse will be d by dt x of s. So if I'm multiplying by factor s, the inverse Laplace will be derivative of x of t, where the initial conditions are assumed 0, that is x of 0 is equal to 0. Similarly, division property, if I divide x of s by s, here you can see, then its inverse Laplace transform will be integral. So integral with time 0 to t x of t dt. So this will be division by s property. Then there are two more properties: frequency differentiation and frequency integration. So I have a function x of s, its inverse Laplace transform is x of t. Then if I differentiate x of s with respect to s, so dx of s by ds, its inverse Laplace transform will be minus t x of t. Similarly, if I have order n, so it will be d raised to power n x of s divided by d s to the power n with order n, then its inverse Laplace transform will be minus 1 raised to power n into t raised to power n into x of t. So accordingly, if the order of the differentiation is different, we may use this formula. If there is a simple differentiation with order 1, then we may use directly minus t x of t. Similarly, frequency integration property, where x of s, its inverse Laplace transform is x of t. I integrate this with respect to, say, with limit s to infinity, x of u du, its inverse Laplace transform will be x of t divided by t. यहाँ पे multiplication में किया था with minus sign. Here it will be divided by t. And very important, the last property of the inverse Laplace transform is very important, and we will be using this several times into the example. Convolution. Convolution is the mathematical way of combining two signals to get third signal. It is an integral that measures the area overlap of one signal x of t as it is time shifted over y of t. Simply, what is convolution? Whenever we perform convolution, it provides you the area overlap by two signals. Two signals are, say, running over to each other, and whatever the area overlap between them will be the convolution. So what is the definition of convolution? Convolution mathematically perform, its symbol is a star. So if I write x star y, it is called x convolved by y. It is minus infinity to infinity, integral of minus infinity to infinity, x of tau, y of t minus tau, d tau. Or we may write here integral of minus infinity to infinity, x of t minus tau into y of tau d tau will be y convolved to x. It is an important tool in studying the response of this system for the given input signal. Why it is important? Because this convolution will provide you the response of the signal. Means if particular input is applied, then what is the output? That will be the response. Very short example I have used after this slide, wherein there will be a GIF image I have taken from certain site, wherein the rectangular waveform is convolved with rectangular waveform itself. So you can see here the convolution of rectangular function with itself. That is, signal f of t is rectangular t. Another signal is g of t, that is rectangular t. And I have convolved this. Forget about the mathematical operations here. But if I convolve rectangular waveform with rectangular waveform, its output is triangular. So you can see there is one blue rectangular waveform over which we are convolving another rectangular waveform which is moving, and while moving whenever it is say come across the blue rectangular waveform, you can see it is coming now. It will touch to the first leading edge to the blue rectangular waveform. Later on area overlap you will get, and accordingly you will get the triangular waveform is the response here. So you can see I cannot stop this video at any moment. If I click it, no, it is a GIF image. So you can see if you calculate the area of the rectangular waveform and the area of the triangular waveform, it is the same. So convolution is providing you the response of particular input. Now here we will move for the mathematics. This is the simple example or animation we can see. Later on we will see the mathematical operation here. So I'll move to the next. So what is the convolution in S domain? Time domain में convolution कैसा है? Time domain में convolution with this formula. Let me erase the ink. So in time domain convolution is X convolve Y, and with this formula of course. But if I go for the convolution in S domain, we'll see what happened. In time domain, determining the convolution of two signals become very complicated depending on the signal. When the signal are transformed to S domain, the convolution becomes very easy. So let's see, by convolution theorem, Laplace transform of x of t convolve to y of t will be equal to x of s into y of s. Here it is a convolution in time domain, but in S domain, convolution is simply the multiplication. So multiplication is easy, you know. And again, if I take inverse Laplace of this S domain, it will be convolution of x of t to y of t. That is, the convolution in time domain becomes the product in S domain. This is true. Sorry, this rule helps in solving many problems related to convolution and inverse Laplace transform. So whatever is easy, we'll always choose easier way to compute, and the answer will be same. We'll have one example to see this phenomenon. So here, convolution in S domain. Find the convolution between t u of t and sine t u of t. There are two signals, this one and sine t u of t. So what is first signal? X of t. X of t is sine t u of t. Then another signal is y of t. Y of t is t u of t. Convolving that together, that is x convolve y, will be integral of minus infinity to infinity. By definition, of course, x tau into y of t minus tau d tau, that is minus infinity to infinity integral sine tau u of t into t minus tau into u t minus tau d tau. So you can see this function. If you want to solve this integration, the calculation are complex. We are not going to solve here. But by S domain, we'll convert into S domain. By X domain, if I convert these together, that is sine of t ut and t u of t, it will be simply 1 upon s square plus 1. Sine of t will be what? S square 1 upon 1 s square plus 1. Let me show you the PPTs that we have already seen. Yes, here you can see sine omega t is what? Omega upon s square plus omega square. Come back to the PPT. We may directly use, no worry about that. Here sin t में omega कितना है? Omega is 1. That's why it is 1 upon s square plus 1. And for the rest of the signal, that is t u of t, it will be 1 by s square. So Laplace transform, it is separated like 1 upon s square minus 1 upon s square plus 1. So if I take inverse Laplace transform of this, that is 1 by s square minus 1 by s square plus 1. So 1 by s square is nothing but t inverse Laplace transform that we have seen already, and 1 by s square plus 1 will get sine of t. So the convolution in time domain becomes very complicated by this equation. But what we did, we convert it into the S domain, then directly made the product of x of s and y of s. Then we get answer in S domain, that is what? Answer in S domain, that is nothing but 1 by s square minus 1 by s square plus 1. And then we have converted this S domain form into the time domain form by using inverse Laplace transform. So 1 by s square will be t minus sine as it is, and 1 by s square plus 1 is nothing but sine t, because 1 by s square plus 1 will be what? Omega upon s square plus omega square. So 1 is nothing but omega, and that is in time domain, convolution in time domain. So you can see the huge calculation we omitted by simply converting the time domain signal into the S domain and say making the product of two signal will be the convolution in the time domain. Okay, one of the advantages is this: the convolution becomes simpler in S domain. This one of the advantage of whatever we are learning, that is Laplace transform, inverse Laplace transform, and so on, conversion from time to S and S to time. Another advantage is solving ordinary differential equation. Solving ODEs in S domain is much simpler compared to solving ODEs in time domain, because ODEs become algebraic equation in S domain. In S domain, ODE becomes algebraic, and that will be easy to solve. For an example, it is ODE is d square x by dt square plus 2 dx by dt minus x of t. Its Laplace transform is s square. Of course, d square x by dt square is s square. Then 2 dx by dt will be s, so 2s, and x of t Laplace transform will be 1, so minus 1. So you can see this is the ODE equation converted into the Laplace transform. It will be algebraic equation into x of s, of course, where x of t is 0 and x dash of t is 0. That is the initial condition we assume supposed to be 0. So Laplace transform easily helps us in convolving, where convolution is just simple multiplication. Laplace transform is applicable to continuous, piecewise continuous, periodic, step, and impulse function. Yes, abhi signals pe we can apply Laplace transform. What those are? Continuous, piecewise continuous, periodic, step, and the impulse. Properties of Laplace transform enables its calculation to be very easy. Of course, why we use a property? Easy conversion and easy calculation. Properties of inverse Laplace transform make it convenient to transform back to the time domain after necessary analysis in S domain. What we do? Time domain will be converted into the S domain. We perform whatever the operation we need, as we did in our earlier example, and later on we may convert it back to the time domain. It will be easier by using inverse Laplace properties. Okay, very simple example. We'll have one RLC series circuit, and there will be ODE equation in S domain. So you can see R, L, and C. Before moving further, I wanted to ask a question. Am I audible? And is PPT visible? Just raise your hand if PPTs are visible. अब तक जो है. Yeah. So everything is going fine. Okay, thank you. Yes, thank you. So solving the example. So R, L, and C are in series, through which I of t is the current which is flowing like this, of course, and V of t is the signal which is applied. Okay. Now here you can see, yes, any question from your end? Omkar, any question there? Okay.
No, sir, no.
Okay, thank you. Okay, now you can see there is no output V0 is shown here. But of course, if V of t is an input, current may be the output, right? So find I of t for t greater than 0. यहाँ पे क्या करना है, हमें करंट फाइंड आउट करना है. Where I of L minus L 0 minus is 0, that is VC. कैपेसिटर का इनिशियल वोल्टेज, इंडक्टर का इनिशियल करंट इज सपोज टू बी 0. V of t is U of t. ये सिग्नल है. V of t is nothing but step U of t. R is 2 ohm, L is 1 Henry, and C is 1 Farad. What we can do here to find out current, of course, we'll apply KVL that you know. It is already done into the network analysis and it must be very, say, clear to you people. Get the dynamics of the system. Dynamic means what happens if particular signal is applied. So how we can write V of t? Yes, ये voltage कैसे मिलेगा? Let me erase the ink first. So ये signal कैसे मिलेगा? V of t. V of t is drop across resistance R, that will be I into R, that is nothing but R I of t. Drop across inductor L, that will be of course derivative of the current, that is L into di by dt. And drop across capacitor C, that will be integral of current with constant 1 by C into integral of 0 to t I of dt. Now this is ODE we can have. Then after taking the Laplace transform, space नहीं दिया मैंने यहाँ पे, Laplace transform, that is V of S is equal to Ri of S plus SLI of S minus initial condition which is supposed to be 0 here, which is given IL 0 minus or 0 plus, whatever it is 0, and I of S by SC. So we converted into Laplace transform and we are interested in current through this circuit. So took current towards left hand side. So I of S will be equal to V of S upon R plus SL plus 1 by SC. Now what is V of t? V of t is a step, that is U of t. सिग्नल हमने दे दिया, अभी हम रिस्पॉन्स देख रहे हैं. सो V of S क्या रहेगा? लाप्लास ट्रांसफॉर्म उसका हमने देखा है अर्लियर पीपीटी में, प्लीज रेफर दैट. एंड इफ पॉसिबल प्रीवियस जो एटलीस्ट पहला लेक्चर है जहाँ पे हमने सिग्नल का टाइम डोमेन से एस डोमेन में मीन्स लाप्लास ट्रांसफॉर्म लिया है, एटलीस्ट दोज पीपीटीज शुड बी इन फ्रंट ऑफ यू during this lecture. So make printout of previous 2 lectures so that it will be easy to understand, because every time I will not go back to the previous lecture. So U of t का Laplace transform है, it is 1 by S. So V of S will be 1 by S. These are the values R2 ohm, L1H and C1F. Putting the values, then I of S will be V of S क्या है? 1 by S divided by R plus SL plus 1 by SC. Multiplying this complete by S, means numerator and denominator, it will be S square plus 2S plus 1, that is 1 upon S square plus 2S plus 1. So simply it is 1 upon S plus 1 whole square. Taking the now we have simplified the ODE by transforming it into the S domain, and later on you need what is the response of this, so we'll convert it back to the time domain. Then I of t will be inverse Laplace transform of I of S, then inverse of 1 by S plus 1 whole square will be e raised to power minus t inverse of 1 by S square, that will be t into e raised to power minus t. So you can see exponential signal है ये. If step input is applied, it is exponential at the output. That is the current is exponential. This is one of the example. We'll go through the another example. You can see here all the initial values are given 0 and current is the output and voltage is the input. So in next example, that is example number 2, we'll solve the similar example. Solve using Laplace transform, where OD is given, that is y double dot, that is double derivative 2y dot minus 8 is equal to 0, where initial conditions are not 0 now. Y of 0 is 3 and y dot of 0 is 6. So we'll take Laplace transform of this ODE, that will be s square plus, sorry, s square into y of s minus initial conditions, that is y dot of 0 minus y of 0 minus 2, this 2 into sy of s minus initial condition, that is y of 0 minus 8 y of s is equal to 0. So y of s will be equal to 3s upon s square minus 2s minus 8. So we got the Laplace transform of above equation and we'll simplify it. So if we simplify it, it will be 3s upon s minus 4 plus s, sorry, into s plus 4, that is a partial fraction. So applying a partial fraction, you can separate it out. Y of s will be equal to 2 by s minus 4 plus 1 by s plus 4. This is simply partial fraction. If you say simplify this again, means if you do the cross multiplication addition divide by complete, say, denominator, you will get this similar answer, this one. So now we have separated it, y of s. So this is a simplified form of s domain, which can be easily converted into time domain. Where to convert into time domain? Whenever you are comfortable with the equation, so that you are, say, quite confident that these all terms can be easily converted into the time domain. There we apply inverse Laplace. So here this function, I'll erase the ink for simplicity again. This function 2 by s plus s minus 4 and another function 1 by s plus 2 can be easily converted into time domain now. That's why this S domain is converted into time domain by applying inverse Laplace transform. So taking y of t will be inverse of y of s, will be taking 2 outside constant, inverse of 1 by s minus 4, and then inverse of 1 by s plus 2. One more time I will go back. It is what? 1 by s minus 4. Another function is 1 by s plus 2. So coming to the conversion that we have seen, इसके print out, please make it ready with you. So what I have is this exponential decay e raised to power minus at, इसका Laplace transform रहता है 1 by s plus a. So what I have 1 by s minus 4. So transform will be e raised to power 4t. Another I have 1 by s plus 2. So it will be converted to e raised to power minus 2t. Same thing is done here. Coming back to the PPT again, current PPT. So you can see here 1 by s minus 4 will be e raised to power minus, sorry, 4t plus 4t, ye 2 as it is, and 1 by s plus 2 will be e raised to power minus 2t. So it is simply addition of two exponential signal is the output. So it becomes again very easy to solve ODE. Any question till the time? If you have any question till the time, you may ask. I'll wait for 30 seconds. If any question, if no, I'll go ahead. Okay, as there is no question from your side, I'll move to the next example. What is a transfer function now? अब तक हमने Laplace inverse Laplace देखा है. What is a transfer function? It's motivation. How to find the response of the system? If particular input is applied, what is the output is nothing but the response. How to find that? For a given input signal, find the response V of t, that is this one. For the given input signal Vi of t, that is this one. What we do earlier, we did apply KVL to get dynamics of the system. First step is this. Again, you can see in earlier example, there was a current which is said output. Current is the output or response. Here we have voltage as an output. So what is the response? So what I can do, I can apply KVL to this loop and I get similar example. Vi of t will be drop across all the components or impedances, that is R, L and C, that is written in this form. Ri of t plus L di of t plus 1 by C integral of I of dt. I of t dt चाहिए था. Okay. Then here V0 of t क्या है? V0 of t is nothing but just the voltage across the capacitor, and capacitor voltage is nothing but what? 1 by C integral of I of t dt. I of t dt. Now we'll solve this later on. Here this is the input. This PPT is only to understand this is the input Vi of t and this is the response V of t that we have to solve for. So the transfer function, to find the time response, we need to solve ordinary differential equation, that is ODE, either integration or differentiation. When the model equations are transferred to S domain, they turn out to be algebraic equation which are easy to solve, that we already mentioned in earlier PPT. The transform model in S domain is called transfer function of the model. It is a model which is applicable for all kinds of input signals. Transfer function for LTI CISO system. What is LTI? It is a linear time invariant. CISO, what is CISO? It is single input, single output. Transfer function is the ratio of Laplace transform of the output, that is called response. Output को हम response कहते हैं, V of t, VO of t. Laplace, what is ratio of transfer function? Is the ratio of Laplace transform of the output to the Laplace transform of the input. Input को हम excitation कहते हैं, which we already seen into the first lecture, with the initial conditions to be 0. Mathematically, if U of S is the Laplace transform of input function and Y of S is the Laplace transform of output function, the transfer function G of S is output का Laplace transform divided by input का Laplace transform, that is Y of S divided by U of S. In certain book it is represented by C of S and R of S. Okay, so please follow the notations whatever you are comfortable with. So the transfer function, this is input excitation, this is output response. Its ratio, output to the input ratio, is nothing but the transfer function of the system. So G of S is Laplace transform of Y of t divided by Laplace transform of U of t, that is Y of S upon U of S. So Laplace transform of output to the Laplace transform of input at initial condition is equal to 0. As an impulse response, impulse signal, that is delta of t. What is delta of t? Delta of t is 0 for say everywhere towards minus infinity to infinity, but at origin it is infinite, is nothing but the impulse signal. And if we take the area of this, if you take very short say or narrow rectangular waveform here, and if you calculate the area of this, that area will become 1. So in impulse signal, delta of t is intentionally narrow and infinitely tall. It integrating to 1, it takes 0 value everywhere except t is equal to 0. Origin पे 0 नहीं रहता है, else everywhere it is 0. And its integral of delta t, that is area, will be equal to 1. That's why इसका response 1 आता है. If the input to the system is unit impulse, if the input to the system is unit impulse, then the output is called impulse response. अगर हमने input को अगर यूनिट इम्पल्स सिग्नल दिया है तो आउटपुट को हमें इम्पल्स रिस्पॉन्स कहना. जनरली हम रिस्पॉन्स कहते हैं, बट अगर ये सिग्नल, this signal is an input to the system, that is called, and whatever the response system is providing is called impulse response. Say u of t is delta of t, the u of s will be 1, so g of s will be y of s. Of course, into this equation, I came back to the previous ppt. Into this equation, if impulse signal is an input, then this u of s become 1, then the transfer function will be what? Y of s. Transfer function will be y of s. That means the transfer function is the Laplace transform of impulse response of an LTI system when initial conditions are set to 0. Impulse response is also called system. I made a mistake while writing this spelling. System response, naturally, it is also called natural response. It is also called free force response. 3 names to the similar thing. System response, impulse response, system response, natural response, or free force response are same. Step to find the transfer function, very important. Find the model equation of the given system. Model equation means where, by what we will get model equation. If it is an electrical circuit, you will apply, of course, KVL, KCL, RCL circuit raha to. If it is mechanical system, you apply Newton's theorem and certain whatever are this theorem. You'll get a what? Model equation. So first step is to find out model equation for getting transfer function. Identify the system input and output variable. Of course, वो हमें जो model equations मिल रहे हैं उसमें input कौन सा और output कौन सा, that we will identify. Take the Laplace transform of model equations assuming initial conditions are to be 0. बाद में हमें Laplace transform लेना है जो भी हमें model equations मिले हैं, and find out the ratio of Laplace transform of output to the Laplace transform of input. ये 4 step जब आप follow करोगे, this one, these all 4 steps, then you'll get the transfer function. We came back to the example that we already have had on, say, previous PPTs. How to find a response of the system if VO is the output and VI of t is the input. Applied KVL to get VI of t. This we already seen. Ri of t plus L di of t dt plus 1 by c integral of I of t dt. Output will be 1 by c integral of it of dt. What is this? These are the model equations. These are the model equations. Next step is identify the input and output. Here input is Vi of t, output is V of t. So identified that. Third step is Laplace transform of the model equation. Assuming initial conditions are 0, Vi of s is this. उसका हमने Laplace transform लिया है Vi of t का. So Laplace transform of this will be Ri of s plus Sl I of s plus 1 by Sc I of s. And V of s ka will be 1 by Sc I of s. And fourth is this transfer function. So where this is what? Input or excitation. This first equation is the input, which is excitation. This is the input excitation. and this is the response or the output. And what is the transfer function? It is output to the input. Laplace transform of output to the input. So V of s, transfer function G of s will be V of s upon V of s. Putting the values here, taking I of s common from this first equation. So I of s get cancelled, and response will be 1 by sc upon r plus sl plus 1 by sc. Simplifying it, of course, by multiplying complete numerator and denominator by sc. So it will be s square lc plus src plus 1. So this is the complete transfer function of the electrical system given above or given in earlier PPT. Okay, what we did here, we considered that VO of t is the output and VI of t is the input. But what if in another circuit, if Vi of t is the input and current I of t is the output? So now we cannot write VO by VT, VO by VI, because now the response is different. That is, output is different. So similar equation, I have Vi of t. V of t निकालने की जरूरत ही नहीं है, because VO से हमें लेना देना नहीं. Identify the input and output variable. Input variable is Vi of t and output क्या है यहाँ पे? Output is current now. In initial circuit, output is voltage. Here it is current. Mohammad Kamran. Mohammad Kamran, any questions? Mohammad Kamran, any questions? Okay, so here you can see, by simply making current as an output, your variable is changed now. The response is current and input is voltage. So taking Laplace transform of the model equation, एक ही equation है यहाँ पे, इसका Laplace transform as it is we took, and then transfer function क्या है? I of s upon V of s, because now I of s is the output or response. So it will be 1 by r plus sl plus 1 by sc, multiplying by sc throughout numerator and denominator. It will be sc upon s square lc plus src plus 1. You can see the difference here. Input parameter or variable is same, but output variable is changed in this example. That's why your transfer function is changed. That's why the second step is very, very important, to identify the input and output variable. If you fail to identify what is the input and what is the output, then definitely your transfer function may get wrong. Next is transfer function of ODE. Find the transfer function of the system described by following equation with zero initial condition. Zero initial condition. So you can see d cube by y d cube dt cube 10 d square y by dt square minus 5 dy by dt plus y will be equal to 10 du by dt plus u. So step 1, जरूरत नहीं है, no need of step 1, because already we have model equation of certain system. Whatever may be the system, it may be electrical, mechanical, or anything. Again, I want to point out one thing. If you have one system which is an electrical system, say RLC circuit, you have another system which may be, say, mechanical system, where force, friction, whatever is there. These two different systems, that is electrical and mechanical, may have similar transfer function. ओके ऐसा जरूरी नहीं है कि मैकेनिकल सिस्टम है उसका ट्रांसफर फंक्शन कभी इलेक्ट्रिकल सिस्टम से मैच नहीं होगा. इट मे हैव सिमिलर transfer function, though they are different in nature. That will be, say, studied later on. It is there in the PPT. further lectures. So first step की जरूरत नहीं है. Second is identify the input and output. Here y of t, generally left hand side, y of t is an output, or y is the output and u is the input. So input and output is identified. Taking Laplace transform of model equation. So taking common, y of s बाहर निकला है. So d क्यूब बाई डी टी का हो गया है s क्यूब प्लस 10 d स्क्वायर बाई डी टी स्क्वायर का हो गया s स्क्वायर माइनस 5s प्लस 1 equal to u of s is taken outside. 10 du by dt, it is 10s. U will be only 1, that will be plus 1. And taking a transfer function, as we have output to input, so it will be y of s upon u of s. So g of s will be y of s upon u of s. So so of course, changing the sides, you'll get 10s plus 1 divided by s cube plus 10s square minus 5s plus 1. This is the complete transfer function of the given system. So any questions till now? Yes, any questions? Okay, so if there is no question, I'll just go through a single slide and later on I'll stop the lecture. Okay, so we have seen this example wherein several examples we have seen wherein we have say understood how to get a transfer function. 4 steps only. मॉडल इक्वेशंस निकालना है, इनपुट आउटपुट वेरिएबल आइडेंटिफाई करना है, उसका लैप्लास ट्रांसफॉर्म लेना है, और फाइनली रिस्पॉन्स टू द इनपुट और रिस्पॉन्स टू द एक्साइटेशन और द आउटपुट टू द इनपुट रेशियो हमें लेना है. दैट इज विल बी ट्रांसफर फंक्शन with initial condition 0, applicable for all kind of systems, maybe electrical, mechanical, electromechanical, physical, whatever. Then the lastly we'll see properties of transfer function. Of course कुछ पढ़ रहे हैं तो वो कहाँ applicable है, क्यों applicable है, what are different properties, rules that has to be known. Now transfer function of any systems, maybe electrical, electronics, electromechanical, mechanical, is independent of the magnitude or and the nature of the input signal. हमने भी ट्रांसफर फंक्शन निकाला है, कहीं पे हमने मेंशन किया है इनपुट इज साइन, इनपुट इज एक्सपोनेंशियल, इनपुट इज स्टेप, डेल्टा? नो, it is independent of the nature of the input signal and the magnitude of the input signal. Using the transfer function, the response can be studied for various inputs to understand the nature of the system. Of course transfer function को हमने various inputs अगर हम दे रहे हैं तो what is the nature of the system, that can be understood. Transfer function does not provide any information concerning the physical structure of the system. As I said, you have particular transfer function, say g of s is equal to 1 upon s square plus 1 s plus 1, and if you have asked question that what type of system is this, is it mechanical, is it electrical, is it electronics, is it physical, ऐसा पूछा है आंसर ट्रांसफर फंक्शन देके, you cannot justify, you cannot identify. Answer is it may be any system, maybe mechanical, maybe electrical, maybe electromechanical, whatever. That is, as I already pointed out, two different physical system can have same transfer function. For an example, below is the example. I have mass spring damper. Later on we'll go in detail of mechanical system. Intentionally I have kept this topic say later on. So mass spring damper जैसे RLC रहता है resistance inductor capacitor, वैसे mechanical mass spring and damper system have transfer function g of s, that is x of s by f of s. F is the force, is the input, x of s is the output. Displacement will be 1 upon ms square plus bs plus k. Values of m, b, k, that is mass, damper and spring constant. Mass, damper and spring constant k is equal to 1. Putting these values here, your transfer function is 1 over s square plus s plus 1. Similarly, if I have RLC circuit, its g of s is v of s upon v of s is say 1 upon s square LC plus sRC plus 1. But all the values R, L and C is equal to say 1. Putting the values, its transfer function will be s 1 upon s square plus s plus 1. So you can see here, I have a mechanical system that is mass spring damper. I have electrical system that is resistance inductor and capacitor RLC. I have both the transfer functions here, and by putting the values, the transfer functions of electrical, given example, okay, transfer function of given mechanical system and the electrical system have similar transfer function. That's why I'm saying if somebody give you the transfer function and asking you the type of the system, you cannot identify, you cannot even guess. It may be mechanical, electrical, maybe electromechanical, anything. So this is all about the inverse Laplace transform, their properties, few examples, its importance or motivation, then transfer function, their steps, how to get a transfer function, some properties of the transfer functions, which will be of course used in further example. Everywhere you will be using these concepts, whatever we learned till now. So this is the third lecture that I have finished. Any question from your side is welcome. Yes, please ask question if you have. I'll wait for 1 or 2 minutes. If there's no question, I'll disconnect this lecture and shortly I'll upload the PPT, whatever we have seen till the time. Anybody has a question? Again, one announcement at the start of the lecture at exactly at 11 o'clock. I have seen only 43 or something, 40 to 50 students have joined the lecture. As the lecture is scheduled well in advance, that is 10:55. So at least at 11 o'clock, I expect all the students joined to the lecture. So if there is no question from your side, see you tomorrow sharp at 10:55 a.m. for lecture number 4. Thank you very much.
Thank you, sir.
Thank you, sir.
Bye.